All right. So let us continue what we were doing. So we started understanding measures of location and variability. We started with measures of basically all the measures of location or variability. These are computed generally from a sample, and they are called sample statistics, and they are set to measure some population parameter. So they are the estimators of any of some population parameter. For example, sample mean is an estimator of population mean, and sample standard deviation can be an estimator of population standard deviation. So whether it be measure of location or variability, uh, it can be a, a point estimator of some population parameter. So we'll talk about mean first. We discussed mean last time, and it's a measure of central location. We call it X bar, and it is an estimator of population mean mu. We can calculate sample mean using this formula. We will add all the observations on the variable X in the sample divided by number of observations, and what we get is the mean of X. Sample mean of X, we call it X bar. Similarly, we can think about calculating the population mean if we have access to all the values that a variable X can take for the entire population. And then if we add all those values and divide it by the population size, capital N, what we get is population mean. Generally, we don't have access to all the observations on a variable in a population, but what we have is a sample, so we cannot normally and generally compute population mean mu. But it can be computed if we have all the data. We took the example of apartment rents and we calculated the mean. It turned out to be 590.8. We added all the apartment rents of all the 70 apartments. Uh, and then we divided the sum of the apartment rents by 70, and we got 590 as the mean rent. Uh, then we discussed about the median. So median of any set of data is the middle value. If you arrange all the values in ascending order, then the value which is locationally in the middle, so that it has same number of values to the right of it and the same to the left of it, then we call that to be the median of the data set. So generally, if we have extreme values in the data, and I showed you with the help of an example yesterday, in that case, median is a preferred measure of central location rather than the mean. So median is preferred to mean. Median generally is reported for annual income because of the fact that income data has extreme values, because there are many people who have very, very high income, and property value data. Uh, the reason why median is preferred to mean when we have extreme values is that if we have values like 2, 4, 2, 3, and then we have a 50, then this 50 is going to affect the mean, but this 50 is not going to affect the median, right? Because in this case, if you put it in ascending order, it will be 2, 2, 3, 4, 50, and median will be 3. So this 50 is not inflating the median. Median remains where it is, 3. It is not inflated. While if you calculate the mean of these numbers, then it turns out that it would be 50 plus 4, 54, 57, 59, 61 divided by 5. So it should be around 12. So mean would be 12. So do you think 12 is a good representative of this data? No, because 12 is not a good representative, because there are twos, there are three, there are fours, low numbers, and there is one high number, and 12 is in the middle of the numbers. While median, which is 3, is a good representative of this data set, because most of the values are of this order, 3, of this level, because we have a 2, we have a 2, we have a 3, we have a 4. All these 4 values are are of the order 3. That means they are around 3. So 3 is giving us an indication that what type of values are there in the data. So median is preferred because mean is affected by large, extremely large or extremely low values, but median is not affected by extremely large or extremely low values. In other words, by extreme values. So you can calculate the median if you put your numbers in ascending order, and if you find the middle one, that would be the median. If you have even number of observations, then you have to take two numbers in the middle, because if you take these two numbers, then only you have three numbers to the left and three numbers to the right. Then you can say 19 and 26 both are in the middle. In that case, you would take the average of 19 and 26, which would be 19 plus 26 divided by 2. So 22.5 would be the median. In this apartment rent example, the middlemost values are the 35th and the 36th value, which is 575 and 575. If you take the average, it would be 575. So 575 is the median, while 590 was the mean, right? So there's a difference between the two in this case. Today we'll talk about trimmed mean. Again, because of the reason that mean is affected by extreme values. So to if you want to if you want your mean to be less affected by extreme values, or not to be affected by the extreme values, and you don't want the median but you want the mean, and still you don't want it to be affected by the extreme values, you can go for trimmed mean. So trimmed mean is a way out of using the mean and not getting affected by the extreme values. So you can do it by deleting a given percentage of the smallest and the largest values from a data set, and then computing the mean of the remaining values. For example, 5% trimmed mean means remove smallest 5% values, remove largest 5% values, remove both of them, and then whatever remains, compute the mean of those values. So that's what you will call a 5% trimmed mean. You can have a 10% trimmed mean, or a 20% trimmed mean, or a 1% trimmed. It depends on what percentage of the values you want to remove from the data set before calculating the mean.
So can you explain this again, please?
Sure. So trimmed mean is a way out for for the fact for the problem that that mean suffers from, and the problem is that it is affected by extreme values. So let us take one example. So if we have 2 10, 12, 10, and then you have 26. So if I ask you what is the mean of x, what would be your answer? Mean of x is equal to sum of x divided by a number of x's. If you add all of them, it would turn out to be 30, 32, 34, 40, 50, 60, 60 divided by 5. Oh, let me make the values even more extreme. So we have a 2 here. Let me make it, this is 34. And let me make it a 66. Right? So 34 and 66 is 100. So 100 divided by 5 is 20. So your mean is 20. Mean of x is 20. Right? Now suppose you can see that you know that there are extreme values in my data. Now these values, I mean, if you arrange these values in ascending order, it would be 2, 10, 10, 12, 66, right? And you thought that I have a few extreme values and I don't want them to affect my mean. My mean is coming out to be 20. Maybe it is because of the extreme values. So let's get rid of the extreme values. So suppose I decided that I would calculate a 20% trimmed mean. So what you would do is you would remove 20% of n values, remove 20% of total values, right, from start and end. So 20% from the start, 20% from the end, that would give me a 20% trimmed mean, right? So 20% of n, 20% of 5 is 1, right? So one value from the starting, one value from the end, remove one value from starting and end. So I'll remove this value and I'll remove this value. And then I'll calculate the mean of 10, 10, and 12. In that case, my 20% trimmed mean is equal to summation x divided by n. And in this case, summation x is 32 divided by 3. And what I get is 3 times 30, 3, 6, 18, 10.66. So my 20% trimmed mean is 10.66 and my mean is 20. So now I'm understanding my data better because I have removed a lot of, I mean, 20% is a huge number, right? I took it for exemplification because it was a number that removed one value from top and the bottom. Suppose you had 100 values, then 20% trimmed mean is a big number. You can take a 5% trimmed mean, remove 5% means 5 values from the top and 5 values from the bottom, and calculate the mean of remaining 90 values. In that case, those 90 values will give you a mean that you wanted, because you got rid of those extreme values. So here in this case, the 20% trimmed mean is 10.66. And here this 10.66 is not affected by extreme values like 2 and 66. Right? So that's the trim mean. You got it? Should I explain again one more time? Any question on this trimmed mean? All right, so let me explain it once more. So we have, let me take another situation, or let me take the data set which is already there. So we have this data set, and you want to calculate 5% trimmed mean. So you want to calculate 5% trimmed mean. And this is your data, right? So there are 70 values. So 5% of 70 is what? Anyone?
It's
It's 3.5, right? So 3.5
35.
3.5 is 5% of 70 is 3.5. So there are 70 values and 5% of 70 means 3.5 values. So remove 3.5 values. Three point five smallest values and remove 3.5 biggest values from the data set. So you want to remove the smallest 3.5 values, then you have to arrange it in ascending order. And this is arranged already. You can see 525, 530, 530, 535, 535, 540, 540, then 545, and then 715. It's already arranged in ascending order, right? So now remove 3.5 values. So you will remove these three values. And then 0.5. So you can take 3.5 to be equal to 4, right? After rounding off. So if you round off 3.5, that means 4. So remove 4 values, right? From smallest 4 values, and then the largest 4 values also. Remove these. So you are going to remove these. They are no more there. They are gone. Now calculate the mean of the remaining numbers. Remaining how many? 448 are gone, so 62 are left. Remaining 62 values. Mean of 62 values would be summation x divided by 62. So you will add these values only. The remaining values, add them up to here, divide them by 62, you will get 5% trimmed mean. Got it? Should I show you? Should I calculate it completely?
No, we got it, I think.
So if you want, I can do it, no problem. But if you got it, then it's okay.
Yes, sir, it's fine.
Right. So just calculate the mean of the remaining 62 values. That would be the 5% trimmed mean. Had it been 10%, you would have removed seven values from seven smallest and seven largest values. 7 of them. So 7 of them would have meant up to here. These many values, the smallest 7 values and the biggest 7 values would have been removed for a 10% trimmed mean. Right? Then the remaining values are, say, are 70 minus 14 are gone, so 56. So sum of the remaining x's divided by 56 would give you a 10% trimmed mean. Right? So that's trimmed mean. And what is the advantage of trimmed mean? Advantage is that when you have extreme values in the data, so there comes the advantage. So that's the advantage, right? Now you don't want your mean to be affected by extreme values, so let us remove them. So once they are gone, you are not affected, your mean is not affected by them. So that limitation of the mean, that it is affected by extreme values, you have dealt with it now when you calculated trimmed mean. Right? So that's the advantage. All right, now let's talk about mode. Mode is the value that has greatest frequency, right? So the value that occurs many times in the data set. But sometimes there are two values which are occurring greatest number of times. In that case, you have a bimodal distribution or bimodal data. You may have a multimodal data if there are more than two modes. So mode is nothing but most frequent value in the data set, right? So in this case, if you see all the values in apartment rents, you would see 550 is repeated 1, 2, 3, 4, 5, 6, 7 times, right? If you see 530, it is repeated twice. 535 is repeated 5 times, right? 540 is repeated 5 times. 545 is repeated 4 times. 560 is repeated 3
So,
times.
what did you say when there's two or more frequencies that is occurring the largest number of times? What do we do then?
Okay, so I'll come to that point after this. So you can see that 550 is the number which is occurring highest number of times, and 7 times it is occurring. There is no other number which is occurring 7 times in the data. So mode is 550, right? And all other values are occurring 6 times or less. But 550 is occurring 7 times. All other values, they are occurring less than 7 times, maybe 6 times, maybe 5 times, maybe 4 times, but maybe 2 times, right? But none of the values is occurring 7 times except 550. So 550 is the most frequently occurring value. So mode is 550, right? Now there may be a situation, for example, in this data set. For example, in this data set, which is the second largest occurring value, tell me. So 550 is occurring 7 times. Is there any number which is occurring 6 times? Can you check it for me? And so on and so forth. So you can see that none of the values is occurring 7 times. The second largest is 5, right? And suppose if I add 2 more 535s here, if I'm adding one 535 here and one 535 here, suppose. So let me add them to this data set. So we have a 535, we have another 535. Now 535 is occurring 1, 2, 3, 4, 5, 6, 7 times, right? In this case, 550 is occurring 7 times. 535 is occurring 7 times. So we have a bimodal data. So we have two modes. One is 550, another is 535. We have two modes here. Then if suppose 535 and apart from these two, 545 is also occurring 1, 2, 3, 4, 5, 6, 7. 545 is also occurring 7 times, suppose. Then we have a multimodal data. Because we have three modes. Modes are three, right? We have a 550, we have 535, we have 545. Three modes are there. So you can have more than two modes, 3, 4, 5 modes. You can have two modes for bimodal data, and you can have one single mode for unimodal data. And in this case, it's a unimodal data because there is only one number which is most frequent, and it is occurring 7 times, and that is 550. Did you get it? You can see the slide also. Just you can have a reading of it.
The slide's not visible yet.
Yeah, it's coming after a lag, so it will be there. Is it there now?
Not yet.
That means there is a huge lag in
Yeah, it's
when.
there now.
So is it clear? Bimodal, multimodal data. Is it clear? So let's talk about weighted mean now. In some instances, the mean is computed by each observation, by giving each observation a weight that reflects its relative position, sorry, relative importance, right? So the choice of weights is, it depends, right? And weights might be the number of credit hours earned for each grade, as in GPA. So it's a classic example of weights. So I'll take this example to explain you because you will understand this better. And you can have quantities like pounds, dollars, or volume to be used as weight. So the basic idea is that sometimes uh, your the values in your data are have some of the values are more important than others. Some of the values in your data are more important than others, right? So you want to assign higher weight, you can assign higher weight to more important values, right? If you do it, that if you assign higher weight to more important values, it means these values would reflect in the mean more than others, right? So the first thing is why you want this weighted mean, because some of the values you think are more important than others. So because you want to give them more importance before calculating the mean, while calculating the mean, so you assign them higher weight, and some of the values are less important. So you assign them lower weight, and the result is that you those values which you assign higher weight are reflected more in the way in the mean as compared to the values which you assign less weight. So it will be clear from an example. If we take one example, it will become clearer to you. Let us see what is their example. Okay, they have used one example. So let us use this example itself. So basically, if you have X, you should have calculated the mean like this, summation xi divided by n. This would have been the mean, right? Now weighted mean is the product of xi and wi, where wi is the weight divided by sum of weights. So these formulas are, corresponding formulas in the sense that in the numerator we are having something which measures the sum of x's. Here we are also measuring the same thing, but it's not the sum of x's, but the sum of product of x's with their weights. And in the denominator, we are taking how many values are there. In here also in the denominator, we are taking how many weights are there, the sum of all weights, right? So let us calculate weighted mean. In this case, it's a very good example using wages. So Ron Butler is a home builder and is looking over the expenses he incurred for a house he just built. For the purpose of pricing future projects, he would like to know the average wage dollar per hour he paid the workers he employed, and listed below are the categories of workers he employed along with their respective wage and total hours worked. So there was a carpenter, and carpenter got $21 per hour as wage, and he worked for 520 hours. Electrician got a wage of $28.72 per hour, and he worked for 230 hours. And laborer worked for 410 hours, and painter got $19.75 per hour. He worked for 270 hours, and plumber worked for 160 hours. So just see the motive of calculating the mean. What is the motive of calculating the mean in this case? Because he wants to price future projects, future homes that he will be building. He wants to price them before building them. So he would like to know the average wage he paid the workers he employed. Because wage is a cost, right? And because wage is a cost, he wants to see what is the cost that he would have to incur. So on the basis of that, he would like to price his future projects, right? He's a home builder. So that's the motive. He wants to use this data, which is already there, the home that he built last year. And now again, he would be building more homes in the future. So he has some data, the real life data. The wages that he gave to different workers and how many hours they worked, right? So of course that there is a house which is say a small house, and now he wants to build a big house, right? So when you are building a big house, there will be more rooms, there will be more carpenter work, there will be more doors, there will be more electrician work, because there will be more sockets and switches, and there would be more laborers who would be working. There would be more painters who would be painting the walls and the doors and everything, and there would be more plumbing work there. So everything will be multiplied, right? So he wants to check that how much he's going to spend on these different heads, right? So basically what he wants is to get the mean wage, right? The mean wage. So he wants to get what is the mean wage of the workers, right? Average wage. So in this case, you can simply, neglect how many hours they worked and calculate the mean wage. If you do it, you would simply add these numbers. When you add them, let me add them. So did they do it? Let me see if they do. No, they didn't do it. So let me do it. So mean wage. Remember, mean wage is mean X, right? X is wage. So let me write it here because W is the weight and W for wage, you might be confused. So wage is X, right? And hours, I'm not talking about hours now. I'm talking about X only. So basically I'm calculating mean wage or I'm calculating mean of X. And this is going to be sum of X divided by 5 because there are 5 X's here. 1, 2, 3, 4, 5. So if you add all the X's, what you get is 5, 6, 7, 14, 13, right? 7 and 6, 13, 3, 1, 7, 7, 14, 22, 29, 30, 3, 11, 4, 12, 13, 22, 26, 2, 2, 4, 2, 6, 7, 8, 9, 10. Divided by 5. So this is going to be 5 to the 10, 5 to the 5, 5 to the 10. So 21.2 is the mean wage. $21.2 per hour is the mean wage of the workers who will be working, who worked in his last project. So he paid on an average $21.2 per hour to the workers, right? Those workers can be carpenters, can be electrician, can be laborer, can be painter, can be plumber. But this is just an average of those wages that he's going to pay. Of course, he is going to pay different wages to different workers. But on an average, for any worker, he would pay $21.2 per hour, right? Do you think it's a good reflection of what he wanted to get? Do you think 21.2 is a good reflection of what he aimed to understand from this? The reason is that because in this calculation, he has assigned equal weight to all workers. He is treating them in the same way. So he is taking no difference between a carpenter and an electrician and a laborer and a painter and a plumber. He is taking all the wages and assigning them equal weights and wanted them to reflect in the mean equally. So that's why we got a mean of 21.2, so that every wage here is reflected equally. But this is not right because somebody worked 160 hours only and somebody worked 520 hours. So the better way is to reflect 21.6 more than 24.16. This is more important. This is less important because this person worked for 160 hours only. So whatever mean wage I want to calculate, I don't want this plumber to be reflecting that much because this is not a true reflection. of the worker's wage. I don't want 24.16 to reflect a lot, because this person will work fewer hours as compared to carpenter. Carpenter is going to work for 520 hours. So most of the wages that I'm going to pay is will be of this order, 21.6. So I want 21.6 to be reflecting more in my mean calculation, because I think this is more important, because this person will work for more hours. So if I make a house which is double this house, then everything will be doubled. So he will be working not 520 hours, but 1040 hours. And this person will be working 320 hours. Then this difference is even going to escalate. It's going to become bigger and bigger. And then you would realize later that you have given equal weight to plumber's wage and carpenter's wage in the mean calculation. So you made a mistake, right? So it's better to give more importance to carpenter wage as compared to plumber wage. So we will see next time. Again, I will talk about this and do the calculations of the weighted mean. Any question up to here?